In section 3.4, we're going to look at finding zeros of polynomial functions. The first topic we're going to look at is the rational zero theorem. And this allows us, for polynomials, to identify all possible rational zeros of the polynomial function. And those will be the factors of the constant term, a naught, divided by the factors of the leading coefficient, a sub n. One thing you'll see when working with the rational zero theorem is that when we list the factors of a number, we do include the positive and negative roots. So if you think of the way the multiples to get 4, it's 1 times 4, 2 times 2, right? So these are the key factors. Notice we'll have this plus or minus symbol for each of those factors. So you'll see that notation here. In example 1, on page 396 of the textbook, we're given this function f of x equals minus x to the fourth plus 3x squared plus 4. So to identify the possible rational zeros, first we'll identify the constant term, which is 4, and then the leading term, which is minus 1. And our possible rational zeros will be the factors of 4 divided by the factors of minus 1. So when we solve this problem, this will be plus or minus 1, plus or minus 2, plus or minus 4, and the factors of minus 1 will still include plus or minus 1. And then we really need to do a division here. Now, when the leading coefficient is positive or negative 1, it's essentially like dividing by 1. So the values that you see in the numerator are really going to be your final answers. Remember, when we come up with a list of possible rational zeros, that doesn't mean that every zero in that list is an actual solution to the polynomial. However, if there are rational zero solutions to the polynomial, they will be contained in that list somewhere. So notice we have 6 distinct possible values. The actual rational zeros are actually minus 2 and 2. Let's look at example 2 on page 397 of your textbook. F of x is 15x cubed plus 14x squared minus 3x minus 2. So again, we want to identify the constant term, which is minus 2, and the leading term, which is 15. So again, our possible rational zeros will be factors of minus 2 and factors of 15. So when we set up these factors, this will be plus or minus 1 and plus or minus 2. This will be plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Now, we do need to do a division here, and you'd like to do it logically. So I'm going to start with this value of 1 here and divide it by all the denominator values, and then move to 2. So when we identify these possible rational zeros, this will be plus or minus 1, plus or minus 1/3, plus or minus 1/5, plus or minus 1/15. And then we'll move to 2. We'll get plus or minus 2, plus or minus 2/3, plus or minus 2/5, and plus or minus 2/15. So these are our possible rational zeros. And there are 16 values. Again, not every value in the list is an actual rational zero solution to the polynomial. And it turns out the actual zeros are minus 1, minus 1/3, and 2/5. So the actual possible rational zeros will be contained in the list somewhere. Now try pencil problem number 1. The next topic in our chapter will be finding the zeros of a polynomial function. This is when we set f of x equal to 0 and solve for the roots, something that we did in section 3.2 when graphing polynomials and finding the x-intercepts. For our class, we're going to just look at third-degree polynomials. We won't look at higher-degree polynomials. In the lesson for this section, I've outlined that you should follow a specific procedure when trying to find the zeros of a polynomial function. First, always try to factor the polynomial and use that factoring by grouping technique. That can save you a lot of time and effort. Very often, some of these polynomials can be factored, and you can find the roots or solutions very quickly. But if it can't be factored, then we're going to use our long division technique that we saw toward the end of section 3.3. Now, how do you get that long division started? Remember, we're going to divide by a divisor in the form x minus c, where c is some root or solution. Now, you can be given that initial root or solution or 0, as we saw at the end of section 3.3. You can either be given it, or you can identify it as an x-intercept from a graph. That way you can get your long division started. You should get a remainder of 0. If you do that, then you can express the polynomial as a product of the divisor and the quotient, and then eventually solve it. However, if you're not given any initial 0, then we have to fall back on the technique we just looked at, which is identify the possible rational zeros, and from that list, those will be the values of c you'll use in your divisor, and you'll have to start dividing the polynomial and looking for a 0 remainder. So there is an element of trial and error in that process. Remember, the list we get from possible rational zeros doesn't mean every value in that list is a true 0. However, if you do divide by an actual 0 from that list, you will get a remainder of 0 in your long division, and then you can solve for the remaining roots. So in this progression, remember, always try to start with factoring by grouping. Then go to long division if you need to. And if you're not given an initial 0, use your possible rational zeros to identify initial 0 and solve the polynomial. Let's look at example 3 on page 397 of your text. So we have this polynomial, f of x equals x cubed plus 2x squared minus 5x minus 6. Now, I would like to factor this polynomial, and we get x squared times x plus 2 for these first two terms, but that's not going to allow us to factor these two terms. So unfortunately, we're going to have to use our long division method, and we're not given an initial 0. So let's find the possible rational zeros. The constant term is minus 6. The leading term is 1. So these factors will be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, all divided by plus or minus 1. So eventually the factors will be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now, when you start to use your possible rational zeros to start your long division, I recommend use the simpler factors and the positive ones. So I'm going to start with positive 1. So choosing this first 0 of positive 1, right, our factor x minus c will be x minus 1. When we go through our long division, eventually what you'll find is that we do not get a 0 remainder. So now we need to try another root. So trying the root of 2, I divide by x minus 2, and when I go through the long division, notice here, finally at the end, we do get a remainder of 0, which is what we're looking for. So what that means is that 2 is now an initial root of our polynomial equation. Now that we found a 0 remainder, remember by the factor theorem, we found a factor for our polynomial, and we can write the polynomial as a product of this divisor or factor times the quotient. So we can do that here, and we'll have x minus 2 times our quotient, and then we can factor this quadratic equation, and then identify our final roots, which in this case, we will get 2, minus 1, and minus 3. And just remember, in solution set notation, they'll be written in ascending order. Let's look at example 4 on page 398 of the textbook. So they've given us another third degree polynomial, f of x equals x cubed plus 7x squared plus 11x minus 3. Now again, you always want to see if you can factor the polynomial. If we pulled out a factor of x squared, we get x squared times x plus 7, but that's not going to allow us to factor this term. So again, we're going to have to fall back on our long division technique and identify possible rational zeros. So the constant term is minus 3. The leading term is 1. So our possible rational zeros are factors of minus 3 divided by factors of 1. That's plus or minus 1 and plus or minus 3 divided by plus or minus 1. So fortunately, we have a sort of a shorter list of possible rational zeros, but really 4 possibilities. Again, I will start with the basic roots from our possible rational zeros. So I perform the long division using a root of 1. So here I divided by x minus 1. And then I took this positive root of 3 and divided by x minus 3. In each of those cases, when you go through the long division, you do not get a 0 remainder. So let's try another root. When trying the root minus 3, our divisor x minus c, remember minus a minus becomes a positive, so minus minus 3 is plus 3. So we'll divide our polynomial by x plus 3, and when we go through that division, eventually we do get a 0 remainder. So now we have found our first initial root of the polynomial, which is minus 3. Now that we've gotten our remainder of 0, by the factor theorem, we can express the polynomial as the product of the divisor x plus 3 and the quotient, which is x squared plus 4x minus 1. Now, unlike the previous example, where we were able to factor and solve this quadratic equation rather quickly, and that's always where you want to start, unfortunately, we can't factor this. But you remember, you can always fall back on the quadratic formula. Remember, when solving with the quadratic formula, always set up the problem carefully. Identify a, b, and c. So we have a is 1, b is 4, c is minus 1. And then carefully substitute it into the quadratic formula. And when we go through this, eventually, after simplifying the radical term, we will get minus 2 plus or minus square roots of 5. And so our final solution set will be x equals minus 3 and minus 2 plus or minus square roots of radical 5. Now do pencil problems 2 and 3. And as a hint, when starting your long division trying different possible roots from your list of possible rational zeros, start at the simpler ones like plus or minus 1.